Okay, so welcome back for part two. This video is going to explore the role of hunger and hormones in obesity and dysregulated metabolism, fundamentally dysregulated hunger. I just want to go back to my first video. So I had this thing in here, which was two concurrent things must be occurring. Something's making us hunger and something is suppressing our metabolisms. And I've been on a really interesting journey that basically has shown two things. One, the whole understanding of the human body and how any of this stuff works is not known. There are so many conflicting pieces of evidence, especially with regards to the microbiome, and the idea that a medical professional would ever say to you, no, you just need to eat less and move more, has become completely insane to me, given that it's just simply not how it works. It is so complex. I think I have a pretty good grasp of how the pieces come together now, but this took so long because I got lost really deep looking at microbiome stuff. And fundamentally also realizing that these two aren't independent things. Typically, the hormones that make you hungry also slow down your metabolism, and the other way around. The hormones that you feel when you have eaten and you're full speed up your metabolism. And so it's not just like when someone loses weight or is trying to lose weight, they can just use willpower to get over their hunger hormones. Their body is actually slowing down their metabolism. The hunger hormone is just the other counterbalance to that. So yeah, let's jump in. So what I did was I wanted to break down hunger, the key hunger hormones and how they work. I'm not going to go into any of these specific studies, but there are these key hormones in the human body, right? You have insulin, glucagon, leptin, adiponectin, amylin, ghrelin, osteocalcin, oxyntomodulin, I got that wrong, PYY, CCK, GLP-1, which everybody now knows, GIP, and something else called the endocannabinoid system, which we're going to jump into. Right? Fundamentally, these things start to get dysregulated for different reasons, and they break for different reasons, and that leads to metabolic disorder, and then that will lead to increased calorie intake or food substrate intake, and then you end up obese. And so there is an interesting and very niche medical opinion, which is there are these glitches in your system that cause these hormones to get dysregulated, and it is the job of the medical system to correct them with hormones. And so that's actually where GLP-1 really was originally being used, is that some unknown glitch was causing your GLP-1 to be out of whack. And so we can add GLP-1 into your system through those injections to like help fix that. And so fundamentally, people who are using GLP-1, Ozempic or whatever properly, they're using it to rebalance GLP-1 because it is dysfunctional, as opposed to what we kind of see in Hollywood, which is people like massively overusing it just to starve themselves. And that doesn't lead to a good place. So insulin, we're just going to run through them quick. Insulin tells your brain that you're nourished, like you've eaten food, and it helps transport glucose into your cells. When you're in a healthy state, when you eat carbohydrates, you should get a big insulin spike, but typically if you're not eating anything, your baseline insulin should be low. And when it's broken, you either have high baseline insulin. So this is like when you're insulin insensitive or insulin resistant, you just have high insulin. So your cells are basically ignoring your insulin. They're not actually taking the things that insulin is trying to sell into the cells, which is kind of how it works. Glucagon tells your liver to release glucose, keep your blood sugar stable, and is in a fine balance with insulin. So insulin and glucagon try and keep your blood sugar stable. When you've eaten, insulin kicks in to like make sure you get blood sugar back down to a level. And when you haven't eaten, glucagon is forcing your liver to release sugar back in. Fine balance. But actually, if you're like messed up, glucagon will spike after food. So not only do you have an insulin spike, which is trying to bring sugar down, glucagon, you can get a glucagon spike, which is trying to shove sugar back into your bloodstream. And yeah, somewhere in there I have, when amylin malfunctions, which we'll get over here, your pancreas can dump glucagon back in. So you end up with high blood sugar, and then you have like this insulin glucagon mix, and you're trying to balance your blood sugar out, but what that actually presents out as a human is like random rampant hunger. And I know for me, when I was keto, you effectively become acutely insulin resistant and glucose intolerant. Whenever I'd eat something sweet, it would trigger like almost a binge eating episode, just because my blood sugar was like swinging around, going crazy. Leptin is basically a hormone that like your fat cells secrete to let your body know how much fat you have, let your brain know how much fat you have, and should regulate your appetite, because you're like, oh, I have all this additional energy. But what actually happens is a lot of times when people become obese, they either have low leptin or they become leptin resistant. So their brain cannot see the leptin flowing through their body. And that is typically because there are other hormones that make your brain able to see leptin. One of them is adiponectin, and one of them is also amylin. When adiponectin is high, it will increase your metabolism, it will increase your insulin sensitivity, and it has an anti-inflammatory role. You don't really want too much or too little, but what you don't want it to be is low always. It comes, if it is low, then your brain will literally be blind to your leptin. So what you want it to do is adiponectin to be high when you have lots of body fat. Your brain can see you have lots of body fat. It speeds up your metabolism to lower that body fat, and also will use that body fat for energy rather than making you hungry. Similar thing from amylin. Ghrelin is the hunger hormone that we know the most. Ghrelin is like, so it signals hunger, and it slows down your metabolism when it is high. So when you wake up in the morning, you're hungry, that is typically ghrelin. And so people will fast in the first part of the morning because when you wake up, ghrelin is at its lowest and then gets higher throughout the day. People end up with like consistently high ghrelin, which is a dysfunction. When you eat, you can end up with like ghrelin pretty shortly after, which is a dysfunction as well. I think it's shown with processed foods, ghrelin comes back really quick, but if you eat whole foods, the ghrelin should stay subdued. And that can lead to excessive hunger. I'm going to skip over the next two. They get kind of confusing, but they're not that specific. So we have PYY, CCK, GLP-1, GIP. These are like the incretins. This is in your small intestine. These are released. And typically it's when you eat, they get released and they say, okay, we're going to increase the metabolic rate and we're going to lower your hunger because there is food and nutrients in the pipeline. And so different types of food will trigger these hormones differently. When you are in a dysfunctional state, which happens with obese people, there is very low secretion of these hormones after a meal, and the half-life of the hormone is really low. So you end up basically eating loads of food and then immediately being hungry, right? It's not about mental willpower. It's like the hormones in your body are signaling that there's no food, even though there's food in your system. And there's lots of reasons why they can malfunction. Diabetes does it, insulin resistance, prolonged dieting. So you can end up with pretty dysregulated hunger hormones if you're always switching from keto to carnivore to intermittent fasting to OMAD to all the different diets. Like you can break your kind of hunger hormone system. And then we get down to the final one, which is your endocannabinoid system. So the endocannabinoid system, I have a whole section about this we'll talk about in a second, but the endocannabinoid system is this like system in your brain and organs that has specifically like two receptors. When the receptors are activated, you get like rampant hunger, your metabolism will slow down, and it has a role in appetite, digestion, metabolism, muscle formation, microbiome regulation. It is a really complex system that nobody seems to really understand, but we have pieces of evidence and studies that like suggest how it might work, and it becomes really, really interesting because it's basically never talked about, but it seems like the endocannabinoid system can sit above and regulate your microbiome. It can also sit above and regulate how GLP-1 is secreted when you eat food. And so it's kind of a master system that a lot of people kind of skip over. So one of the things I then did was I was trying to tie this back to the individual hormones back to seed oils or high-linoleic acid diets to try and understand, like if you eat this novel thing, which I won't even call a food item, what happens? And what we found was, so seed oils will induce acute and long-term insulin resistance, so that breaks that hormone. Linoleic acid acutely stimulates glucagon, so it breaks that hormone. Maternal high linoleic acid diets will increase circulating leptin in the female offspring. That's in a mice model, and also saw that 4-HNE, which is the main lipid peroxidation product of linoleic acid, will inhibit leptin signaling. Maternal linoleic acid diet decreased circulating adiponectin in male mice, so it starts to break something there. Again, those are my studies. So we do know when you ingest PUFAs versus like olive oil or lard, which is a higher saturated fat, but lard's contentious, it will trigger the lowest GLP-1 response, which is the thing we like to talk about. So you've eaten something which with the same level of calories would just literally like not signal the same hormone that says you've eaten enough calories, speed up your metabolism, lower your hunger. And then with the endocannabinoid system, I will take a skip there and go into some more detail. But one of the really interesting things about the endocannabinoid system you need to think about is you can activate these receptors and you can block these receptors. We've seen that when you block the receptors, you end up with akkermansia, larger akkermansia populations, which are like a good microbiome population, which actually I think is highly linked to GLP-1 secretion. Also, we talk about like the munchies, endocannabinoid. We have when you have THC of the right strain, it will piss off your CB1 receptor, I think, and that's what like induces the munchies feeling. Yeah, we've seen when you block this system, basically you can increase metabolism, weight loss, and the flourishing of good gut bacteria and the reduction of bad gut bacteria, which is an insane idea that like neurons in your brain can control that, but I do get that later on. Fundamentally, I have looked at this through a seed oil lens, but if we look at these as like the dirty dozen, I don't even know if there's 12 of them, in a state of lean, healthy homeostasis, these hormones are like being orchestrated in a very complex way, and we've seen if you add in seed oils, that all starts to break when you go down. Ding, 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 ding. Every single one of them pretty much is like broken by ingestion of seed oils. So we're at the 10-minute mark. I'm going to jump over to endocannabinoid. So as I was saying, the endocannabinoid system is these like two receptors. They're in your brain and in your organs. And when you activate them, they will make you hungry. They'll lower your metabolism. They'll do some kind of crazy stuff, and when you block them you can have better outcomes. And so we're going to just look at like some of the literature around that. So I'm going to be switching between these two windows in a second. So the first one I wanted to look at was role of cannabinoids in obesity. So in this study we basically discovered that the CB receptors can regulate thermogenesis, which is like how much heat you produce, like your metabolic partitioning to heat, food intake, inflammation. If you block CB1, you can induce weight loss and improve blood lipid parameters and increase adiponectin, right? So we know that if you have high fat, you want higher adiponectin to like block off and to signal that you, I'm sorry, I just got a phone call and totally messed it up. CB2 stimulation increases thermogenesis and raging of fat, which is like a little separate. So in an ideal world, you want to block CB1 and you want to activate CB2, or do them kind of independently of each other. But that was in this study here. So let's jump back here. So we know that there's something going on here. So then we have this one, which is fatty acid modulation of endocannabinoid system and the effect of food intake and metabolism. So you have two things that basically can activate your CB1 and CB2 receptors. Something called 2AG, and I'm going to get the other name wrong. But basically, we discovered that in this paper here, we've discovered that. So you have AEA, that's the other thing, and anandamide. I'm not going to say it right, but we've discovered in this paper that in obese individuals, you have much higher like circulating endocannabinoid activators, let's call them, than in lean people, and that your endocannabinoid system is activated by dietary linoleic acid. So fundamentally, AEA, which I can't say the long word for it, AEA comes from linoleic acid in the diet. It comes from arachidonic acid, and then above that, linoleic acid, which is your safflower, your sunflower, your soybean oil, your canola oil. So let's jump down here. So this one's really interesting. Endocannabinoid receptor 1 and sympathetic nervous system mediate the beneficial metabolic effects of gastric bypass. So a gastric bypass is, am I going to have a diagram here? Yeah. So gastric bypass is where they like cut this hole in your system and they basically skip your stomach down to your intestines so that your food goes straight into your intestines and not go through your stomach. And what they found, literally like years after doing gastric bypasses, and they worked and they couldn't quite wonder why, versus a sleeve gastrectomy, which is where they shrink your stomach, they found that it was down regulating your CB1 expression, and it increases your metabolic rate and also browns your fat. So that would suggest that it is activating CB2 and then blocking really CB1, or hiding the CB1 expression. So like literally 30 years after the gastric bypass surgery has been conducted, they're like, oh, it turns out it increases your metabolic rate, which doesn't make any sense other than to be messing with the ECS. And then they did a number of studies with mice to try and mimic the effects, and they found like perfect mimicry by using this drug rimonabant, which we're going to talk about in a second. But that's a CB1, like blocks your CB1 receptor, and in theory is actually the most successful weight loss drug in the history of the human race. But we can talk about that one in a little bit. So then we had another study here, which is dietary linoleic acid elevates endocannabinoids, 2-AG and anandamide, and promotes weight gain in mice fed a low-fat diet. So they took these mice and they gave them the same level of calories in their food, and one diet had 1% linoleic acid, and one diet they moved up to 8% linoleic acid in the diet. And the group that ate the 8% linoleic acid ended up having increased weight gain, and their actual fat cells were larger. So that increased the capacity of them to then get fat. They interestingly added omega-3s, and something else like weird happened. I won't go into that here, but this is like a repeated behavior that we see in humans and mice. So that one is in here. I realize I don't actually need to jump into it. So we jumped over to this one, which is a Western-like fat diet is sufficient to induce a gradual enhancement of fat mass over generations. This is in mice, but they did something really interesting. They basically increased the amount of linoleic acid, so omega-6, they started eating by an 0.6-0.3 ratio of 28. And then they randomly mated these mice. And over 4 generations, they showed every generation they had increased fat mass, which is basically was from them both like having, no, I'm going to misunderstood that word. Anyway, they had increased fat mass due to combined hyperplasia and hypertrophy. So I think that's like more fat cells, and the fat cells are much larger. But the food intake was kept the same in every generation. The only thing they did was they increased this linoleic acid, which is like every boxed packaged goods in the supermarket has this in it pretty much. Every fried food is this. Every fried chicken, every restaurant, every takeout box is high linoleic acid. So like, quite honestly, nothing else could have changed in our environment other than increasing linoleic acid, which we know has happened from my previous video. I can show the graph. And over generations, people got fatter, and these mice got fatter and fatter and fatter. So it's not necessarily like somebody born today starts with net neutral and then can become obese when we're wondering why the obesity rate is increasing. Like, it is generationally increasing through, I think that would be epigenetics or like a microbiome change. So then we came here. Blockade of CB1 cannabinoid receptor alters gut microbiome and attenuates inflammation and diet-induced obesity. That's this study. So they block the CB1 receptor, and what they found was that there's a dramatic increase in relative abundance of Akkermansia, which is the good bacteria, one population of good bacteria in your microbiome that is related to GLP-1 secretion when you eat, and decrease these 2 other populations, which are known as bad populations in your gut, which is mental to me, that we block a receptor in your brain and organs and your gut bacteria changes. There is a really, really interesting explanation for why that is. I've now like come to understand that. But fundamentally, there's a piece with the microbiome at play here, and also that is actually driven by your ECB, your endocannabinoid system, ECS, in this is what this one is suggesting. So then we know at that point, we're like, cool. So we want to avoid things that annoy your CB1. Ideally, we want to block CB1, and activating CB2 is also probably a good idea. That will help brown your fat, which basically turns white, useless fat into like metabolically active, heat-generating fat cells. This one, they took CBD and then they basically fed it to people, and they discovered that CBD itself would just promote the browning of your fat cells. So CBD itself is likely going to be blocking CB1 and activating CB2 receptors. Then there was this study in humans, weight loss and therapeutic metabolic effects of THCV infused mucoadhesive strips, and they basically gave humans in this trial these like strips to suck on and digest with CBD and THCV, which is like the non-hallucinogenic version of THC. It's my absolutely stupid way of explaining that. And the mechanism that it blocks the CB1 receptor. And in a 90-day trial of humans, they found that the trial group had a 9-pound weight loss. Nothing else changed in their life. They just said, hey, take this strip. And the placebo lost effectively zero pounds, which is like a pretty mental idea for weight loss. So there's something there around blocking your CB1 and activating your CB2. And then third study is this one. So anandamide, which we discussed up there, that comes from arachidonic acid, which comes from linoleic acid, which is all polyunsaturated fat. There are versions of the same thing, but they come from saturated fat and monounsaturated fat, and they are stearoyethanol, I can't say that one, and oleoethanolamide, I can't say that one, which is mono, and then there's palmitic ethanolamide, which is another saturated fat one. And we basically did this thing with mice where we gave them that and starved the mice, discovered that both the PEA, which is palm, and SEA, which is this one, decreased food intake in starved mice. So they're already starved, and then they gave them these, like, they're not classified as endocannabinoids, but they're like endocannabinoid adjacent molecules. So they actually described it as the SEA. They described it as an anorexic effect in mice. Now, the mechanism of that is really unclear. Those things don't seem to block or activate CB1 and CB2. If anything, they just kind of prevent linoleic acid from activating CB1. But fundamentally, if it wasn't clear that like dietary linoleic acid is all you need to create these endocannabinoids and trigger this system. So one of the questions that comes up from this space is like, well, why don't we use why don't we block CB1? Why don't we do blocking CB1 for a pharmacology intervention rather than bariatric surgery or gastric bypass, which we saw that image of? And that's like actual surgery. You have to cut into somebody and move it along, like move the organs around and have that change for them, which seems very intrusive. And it's a good question. There was a drug called rimonabant, which came out probably 17, 20 years ago, that blocked your CB1 receptor and was enormously successful. When you take it, it blocks CB1, your fat cells get browned, people miraculously had lower hunger, they dropped weight, their metabolisms increased, so it wasn't like endless starving. It was, the metabolism was increasing, the fat was browning, the gut biome got regulated back into like healthy populations and reduction of unhealthy populations, and they pulled it because it had a suicide risk. They thought it had an outsized suicide risk, and they pulled this drug from the market. And the wild thing is, which is how I'm ending this video, when 17 years later they went and looked at all the data, and they actually discovered that when you were taking the higher dose, or the highest dose, the in 1,000 suicide attempt risk is less than 1 in 1,000. It's about half in 1,000. It is lower than the placebo group, and gastric bypass, it is way lower than gastric bypass, which is effectively 3 in 1,000 people commit suicide, and then there's an even higher self-harm rate. So there begs questions there, and I think this is an interesting piece when I was looking at this stuff, was trying to understand GLP-1 drugs. The GLP-1 drugs are like, we've been using them for 20 years, but because we've never really looked at them with enough fine scope, and now we are, as they're so massive, the mechanisms by which they work, we don't have a full understanding of how they actually work. We just keep discovering more and more things. Like GLP-1's hunger. Well, actually, it raises your resting metabolic rate, which is like a twofold craziness. So if you take too much and you're not eating anything and your metabolic rate is increasing, you're going to catabolize muscle tissue and all the cartilage in your face and all of the other pieces for energy substrate inside your body. But also we're finding that people who take GLP-1 end up with like higher rates of depression, because it's not that food gives them joy, it's that clearly these hormones, these systems regulate mood, depression, hunger, right? Like the way in which certain parts of cannabis or marijuana can cause depression is likely done through the endocannabinoid system. Anyway, this is my messy follow-up video to what makes people obese and how do we cure it. I have read enough about the endocannabinoid system that, like, to me, this is dead to rights. The microbiome stuff gets really confusing, but this role in the microbiome makes it really make sense to me. And fundamentally, what we're looking for is what happened to lower metabolic rate, increase hunger, and have a intergenerational cascading effect Well, we've seen here, seed oils fuck up your hormones, seed oils fuck up your endocannabinoid system, and they successively break generations further and further and further, which is pretty crazy model. Anyway, that's my current take on the hunger, the hormone stuff. And I think there's some further stuff you can look at here in the cannabinoid system and reward and like hedonic eating. I've had a number of discussions with obese people or people suffering from obesity who are talking about, no, it's not that. It's definitely not that. It's like, I got emotional and I ate all this food. And you're like, that, if you had a fully regulated hormonal system, you wouldn't have been emotional, and like food wouldn't have been an answer, but it's likely something to do with the endocannabinoid system. Anyway, the next steps for me are likely, okay, if this is what's causing it, how do we undo it? And I'm going to run some personal experiments, taking some THCV and see what happens. And yeah, thanks for listening. Appreciate all of you.